welcome everyone. Welcome to the RASC Edmonton Center monthly meeting. I am your president and host, Jay Lavender, and it is 7:31 and I will call the meeting to order. We have a pretty exciting speaker lineup tonight, which is great. A couple of little housekeeping items to get rid of first. And then once we do that, we will get on to the good stuff. So I think for now, we have posted the members' meeting minutes to the OneDrive from the February meeting. And I'm wondering if there were any errors or omissions. Anyone? Okay, hearing none, we'll hand the microphone over to Madam Secretary.
I move that the meeting minutes from the February 13 meeting as posted to the OneDrive be accepted.
Thank you, Daisy. Do we have a seconder? Kent Martins, seconds. All those in favor? All right, that motion is passed. Thank you very much. Okay, second item on the list there is just the treasurer's report from Jeff Whiten. If you could just click that up. Hopefully it works. There we go. Jeff.
Thank you. So very little activity through the accounts this last month. It was a quiet month. Our general account is unchanged in February. Any questions?
Any questions? All right. Thank you, Jeff. Appreciate that. Sharon, you want to introduce our guest speaker?
Thank you very much. I'm very happy to introduce our next speaker. This month's featured speaker is Nassim Bozorgnia. She's one of the newest professors in the Department of Physics at the University of Alberta, and she's an expert on dark matter. And while many people in our department actually are experimentally looking for dark matter, she focuses much more on the astrophysical side of dark matter. She did her PhD at University of California, Los Angeles, and then she was a postdoctoral researcher in Germany, the Netherlands, and the UK before coming to Canada, where she started actually at York University in Toronto. And just this last September, she started at the University of Alberta. She basically, we managed to convince her to move here. So I'm really happy to introduce her. And do we have? Okay, we're going to share her screen, and I think you can come on up. Thank you so much.
Thank you very much. Okay, thank you very much, Sharon, for the very nice introduction. So today I want to talk about what dark matter is basically and how what role it plays in our universe and the structure formation in our universe. All right, so let's start with first one simple question. What is the universe made of? So if you consider all the atoms which make up the elements in the periodic table and they make up our bodies, plants, planets, the stars in the universe and all the galaxies that exist. So all of these make basically the ordinary matter in the universe. And if you consider the matter and energy that exists in the universe, ordinary matter is just around 5% of the total matter and the energy which exists in the universe. You can see here in this chart that about 27% is in the form of this mysterious dark matter, which only we know that interacts gravitationally, but does not interact with light. And about 70% or 68% is in the form of this unknown energy called dark energy, which is responsible for the accelerated expansion of the universe, and we know even less about. So in this talk, I'm going to focus on this 27%, which is the dark matter content. And actually, if you consider only the matter in the universe, dark matter makes up 85% of the total matter in the universe. So ordinary matter, everything we are made of, is just 15%. 85% is in this form of unknown dark matter, which we don't really know much about its nature. So dark matter has quite a long history. So already in the late 1800s, early 1900s, the British physicist Lord Kelvin tried to estimate the mass of the galaxies from the observed velocities of the stars. And he found that there are some discrepancies with the mass of the visible stars. So he actually has a quote saying, many of our stars, perhaps a great majority of them, may be dark bodies. And then following up his work around the same time, French mathematician and physicist Poincaré also became interested in what Lord Kelvin was doing. And he was actually one of the first people who used the term dark matter, of course, in the original French, in 1906. So it really does have a very long history, and you can now kind of move forward in time, looking at the evidence of dark matter basically coming from modern observations. And this evidence comes from a variety of different observations, from scale of small dwarf galaxies to larger galaxies like the size of our own Milky Way, to then clusters of galaxies, which actually include hundreds to thousands of galaxies, and then up to the largest scale structures that we have in the universe. So we have the evidence for dark matter from all of this. And I'm going to briefly go over some of the important evidences that we have for dark matter. And we can start from galaxy rotation curves, which is one of the important ones. So these measurements actually of the velocity of stars around the galaxy, this was pioneered in the 1970s by astronomer Vera Rubin and collaborators. And at that time, she measured the velocity of the stars as they go from the center of the galaxy to outskirts of the galaxy. And what she and her collaborators found was that actually, as you go from the center of the galaxy, as you get away from the center, what you expect from just the laws of physics is that the velocity of the stars, rotational velocities of the stars around the center of the galaxy, this should start to decrease as you go to the outskirts of the galaxy and beyond where the luminous galaxy ends. What they found instead was that as you basically go beyond where the luminous galaxy ends, you still have some large velocity for the rotation of the stars. So they are rotating quite fast, actually, still where there's no more, you don't expect any more luminous matter to be. So you can also see it here in this little movie. So what we expect for the rotation of the stars and gas around the center of the galaxy, this is the speed that we expect, but this is highly exaggerated, of course. But what we observe is, the one on the right. So this is basically telling us that there should be some mass that we cannot see beyond the visible galaxy. So way beyond where the visible galaxy ends, we should still have some invisible mass, which is causing this faster rotation of the stars and gas. And so what we know as a galaxy, which looks something like this, we believe it is actually embedded in a large sphere of this unknown and invisible matter, dark matter, which can have a radius which is more than 10 times the radius of the visible galaxy. And actually, if you could see the dark matter in the galaxy, so this is called the dark matter halo, but if you could see the dark matter, we also expect that there is a lot of substructure that exists, and it's all dark, we don't see it. But simulations of galaxy formation tell us that there should be a lot of these smaller clumps of dark matter around the galaxy as well. And they're not stationary, they are all moving around the center of the galaxy. So this is showing you one of these simulations of galaxy formation with dark matter. And if you could see the dark matter in our galaxy, it would look something like this. So there's a lot of this structure which is moving and rotating around the center of the galaxy. Okay, so one of the other evidences for dark matter comes from the observations we have and the computations we have from gravitational lensing. So what is gravitational lensing? So if you have some galaxy cluster, for example, as shown in this image, where you have hundreds of or thousands of galaxies clustered together, this has a large mass. And so basically, Einstein's theory of relativity tells us that the light that would be coming from some source or a galaxy which is beyond this galaxy cluster, this light would be actually curved until it reaches us, because this mass of the cluster is actually curving space-time. And so you will have some distortion in the image of the galaxy that you would observe, the galaxy which is behind this galaxy. And so we have a lot of examples of this gravitational lensing already from observations. So this is some example. This is a cluster, Abell 370, and this is one of the first observations we have by the Hubble Space Telescope of gravitational lensing. So this galaxy cluster is about 5 billion light years away from us. So the light takes about 5 billion years to reach us from this cluster. And then there are a bunch of galaxies which are behind this galaxy cluster. So when we're looking at them, we can't directly see them. But this large mass of the cluster actually distorts this light from these galaxies. And you see these arcs happening here and some distortions also of the light happening. And this is, you can compute based on these distorted images how much matter there is actually in this cluster, what is the mass of this cluster, and you can find that there is substantially more dark matter than luminous matter in the cluster. So this is another important evidence for dark matter. So the most compelling evidence for dark matter, in my opinion, comes actually from the bullet cluster. So basically, this is the collision of two galaxy clusters. And what you see here is two different colors. So the parts which are colored pink is actually the hot gas in these two galaxy clusters, which is detected in X-ray. And then via gravitational lensing, you can figure out where most of the mass in these two clusters are. And you see that they are not at the same place. So it might be a little bit hard to see here, but you have these blue parts here on the right and the left, where most of the mass of the two clusters that have collided are, and this is different from where you actually see the luminous mass in X-rays. And the reason that they are basically divided like that is that the hot gas actually is slowed due to the electromagnetic interactions that it has during collision, whereas the dark matter is collisionless and it does not slow down. It basically moves quite fast, and you see that it's quite separated from where the hot gas is. So this is quite a strong and important evidence for dark matter. And since the bullet cluster observation, we have also multiple other galaxy cluster collisions that have been observed, and you see the same effect happening in all of these other cases as well. So moving on to larger scales. So this is the cosmic microwave background radiation. So this is really a snapshot of the baby universe. If you could take a picture of the universe when it was only 380,000 years after the Big Bang, you see these temperature fluctuations, and the different colors is just hotter or colder regions that you have in this map. And what this is actually showing, so this is really the oldest electromagnetic radiation we have in the universe. And the reason that we are seeing these light actually now is that, and this comes from this about 400,000 years after the Big Bang, is because before this this time, you had charged particles in the universe. You had this plasma of protons and electrons moving around, and the photons were trapped there. They couldn't escape. And so the universe was not transparent. Around that time, neutral hydrogen atoms formed, so universe became neutral, and so the photons could escape finally, and the universe became transparent. And these photons actually fill the entire universe today, and they create this, it's almost uniform background. It's not completely uniform, but you saw that there are some temperature fluctuations. These are quite tiny. They're in the order of 1 part in 100,000 across the sky, so tiny fluctuations. But the point is that this pattern of the fluctuations from this pattern and a really precise measurements of this pattern tells us actually the amount of dark matter that exists in the universe. So this 27% that I mentioned before comes very precisely to the percent level from the CMB measurements. And it's really an overwhelming evidence for dark matter, which is quite important and interesting. So let's see if we take this information we have from cosmology, the CMB, the amount of dark matter and the amount of ordinary matter in the universe, we can start to simulate our universe starting from time very close to the Big Bang and let the simulation run. So this is actually showing you the time after Big Bang, so 0.5 billion years, and it keeps going on. And what you're seeing here is the density of dark matter. So the lighter colored parts are densest. And then you see that just under the force of gravity, dark matter clumps together and these structures start to form. And so dark matter is responsible for structure formation in the universe. And if it did not exist, we didn't have this mass, we wouldn't have the galaxies that we see today and we wouldn't be here. So it's quite exciting. And so now the simulation has switched to ordinary matter or gas. So different colors are different temperature gas. So gas actually falls in the gravity or the gravitational potential of these dark matter structures, and then it cools and forms stars and galaxies start to form. And then you see these heat waves at where you have the supermassive black holes and active galactic nuclei in the center of the galaxies, and all sorts of structures start to form. And so you see again the time here, this is about 6 billion years after the Big Bang. And if you let this simulation run until today, you basically can see a lot of simulated galaxies which look a lot like our own universe and the galaxies in our own universe. So you need dark matter to form these galaxies the way that they are. So this is another simulation and another example focusing on a smaller region and one galaxy and comparing dark matter, gas, and stellar light. And you see that there is not much going on in the stellar light parts yet, but you have a lot of structure in dark matter and it's starting to form. So you basically have your galaxy here, you have a bunch of other galaxies forming and merging with the main galaxy. So this is how our galaxy actually acquires more mass, because you have a lot of other galaxies throughout time merging with it. This is also the time since the Big Bang. And then you also see what is happening in dark matter and in gas. And if you let this again run, you end up with a galaxy which looks a lot like our own galaxy, but you have beyond where you have the stellar light, you have a lot of dark matter still there. So this is again an interesting example of how dark matter is responsible for forming these galaxies. And so now we are at 13.8 billion years after the Big Bang, and we have the galaxy here. Okay, so to understand what the nature of dark matter is, or try to actually understand it, let's first try to see what are the building blocks of ordinary matter. So let's start with the standard model of particle physics. So this is all the matter and interaction that we have in particle physics in ordinary matter. So you see that here we have quarks, we have leptons, and then we have these force carriers. So let's look in a little bit more detail into this. So we have 6 types of quarks: up, down, charm, strange, top and bottom. The mass increases as you go from the first column to the next and to the one to the right. And basically, if you want to see what a proton is made of, is 2 up quarks and a down quark. A neutron is 2 down quarks and an up quark. And then if you put these together, you can make a nucleus of an atom and then add in some electrons and you have your atom. So, so this is basically what the matter, normal ordinary matter, and most of us are made of. And then you have also these other particles here. You have for the leptons, you have electron, muon, tau, and their respective neutrinos. And the second and the third column here, they become a bit so they're not as stable, so they basically decay back to this first column. And so most of the material matter that we see and everything is made of these first column particles in the first column. But you also have these force carriers here, which are in charge of the interactions between the different particles. So the photon is in charge of the electromagnetic interaction. Gluon is what glues together basically the quarks in the proton and neutrons. And then the Z and W are in charge of the weak interactions, which, for example, fuels energy in the sun or happens when you have radioactive decay. And the Higgs, which was discovered by the Large Hadron Collider in 2012, is responsible of giving mass to all of these particles. So just to see briefly how this electromagnetic interaction, for example, works, you have 2, I cannot move this a bit further. Okay, so you have 2 electrons which are interacting here. And so one of them would basically emit a photon in a second, and the other one would absorb it, and then they basically both get some velocity and they recoil away. So this is the repulsion of 2 electrons and electromagnetic interaction happening here with the exchange of a photon. Okay, so this is all the usual ordinary matter. So what about dark matter? So we basically don't know what the nature of dark matter or any of its non-gravitational interactions are. So all of the evidence that we talked about for dark matter, it comes from its gravitational interaction with ordinary matter. We know that none of the particles in the standard model of particle physics that we just talked about can be the dark matter particle. So we need a particle that is neutral, so it doesn't interact electromagnetically. It has to have mass, and it has to also be long-lived, so that we have the particle, if it was produced in the early universe, we should still have it around today because we see it, it's evidence. So we basically need to go beyond the standard model of particle physics to be able to have a candidate for dark matter. And we are not short of ideas. So there is a lot of well-motivated dark matter candidates. And so here is just showing you a range of, the theories that theorists have come up with for what dark matter can be. And this is basically showing here, these numbers are showing you the dark matter mass and the range it can have. So just to put this in context, the mass of the proton is here in this diagram, and then the dark matter could be much lighter than proton. So there are some theories that dark matter can have a mass which is the proton mass divided by a 1 followed by 30 zeros. So this is 10 to the 30. So a proton mass divided by 10 to the 30. So it's quite light, or it could actually have a few solar masses. So it could be a large object like the sun, and which these are called primordial black holes. So this can be another type of dark matter. Now to consider actually, well, there is a lot of theories here, models for dark matter. So where do we search and how do we search for this? So let's focus on this range basically, which you consider dark matter to be a particle. So it's still a sort of elementary particle, or it could be some composite particle made of some other elementary particles, which is not part of the standard model. But this range of candidates, these are called weakly interacting massive particles. And they're one of the most extensively studied class of dark matter candidates beyond the standard model of particle physics. And the reason that they are interesting is that if you have in the early universe, you have dark matter particles interacting and annihilating to usual ordinary matter or standard model particles. And if they are made of these weakly interacting particles, this would automatically produce the correct abundance of dark matter today. So this is a motivation for these WIMPs. And the mass of these particles can be between 1 to 10,000 times protons mass. And the other interesting thing is that we can experimentally search for them. So there is actually a huge experimental program to search for WIMPs. There are 3 complementary ways we can search for this: indirect detection, collider searches, and direct detection. So I can briefly talk about each of these and see what is needed to understand actually if dark matter is detected in one of these to try to understand the nature of dark matter. So let's start with indirect detection. So if you have, again, 2 dark matter particles interacting and producing 2 standard model particles, you can actually search for these products, standard model products, using ground-based or space-based telescopes. So this might be happening anywhere in our galaxy, but especially at the center of our galaxy, which we think that there's the most of the dark matter is there, you would have dark matter particles annihilating. And one of the particles they could go to is actually high energy light or gamma rays. And so they can produce these gamma rays in our galaxy. So this is basically showing what is the expected gamma ray flux from the dark matter annihilation. And this is coming from some simulations. And this depends obviously on the amount of dark matter throughout the galaxy. So we have the maximum here in the center because the simulations show us that the maximum amount of dark matter should be in the center of our galaxy. And then the density of dark matter just decreases as we go to larger radii. Now, so this is a signal that we would be searching for in the gamma ray, looking at the observations of gamma rays. But we have a lot of astrophysical background. So this is the actual gamma ray sky. This is measured by the Fermi Space Telescope. And so this is just coming from, so you see that there is a lot of background. So this is the Milky Way disk, and you have a lot of point sources here, active galactic nuclei, pulsars, all of these produce gamma rays. So if you want to actually figure out where dark matter is there and what is the signal due to dark matter, you have to first have a really good understanding of the gamma ray background. And this is quite difficult, but a lot of work has gone into this. And actually, a few years ago, there was a hint for a signal from the center of the galaxy in gamma rays, which was quite interesting, but it hasn't yet been confirmed. So, and it hasn't gone away either. So this can be something interesting that still we are trying to understand these gamma ray backgrounds and try to model this quite well to understand if it's due to dark matter or some astrophysical background. Then the next way to search for dark matter or to search for WIMPs is to produce them in colliders. So you can actually take the same interaction I showed you, but the inverse of it. So you take 2 ordinary or standard model particles, and then they can produce dark matter particles in your colliders. And this is actually showing you the Large Hadron Collider, which is this, you have this 27 kilometers tunnel underground, and it's between France and Switzerland. And what you search for actually in this colliders is the dark matter. The standard model particles can produce dark matter. Dark matter would just go away, scatter away from your collider, and you search for some missing energy in the data that you have in the colliders. And just to show you how this works, so what these colliders, this Large Hadron Collider is doing, basically you have two proton beams, and they are boosted first to get speed, so their speed increases to around the speed of light, and then they smash these two protons together, and then you have 4 detectors there, Atlas, CMS, LHCb, and so on. And so this is basically showing you the trip, the journey that the proton takes underground in the tunnel. And each of the proton is made of the 3 quarks. You see it there. You have one proton beam coming, and another one is coming from the opposite direction. And they basically collide. And then you have a bunch of events and particles there, and they could be producing dark matter. So this is where they collide in one of the detectors. And you might have dark matter produced there. It will actually escape. It doesn't interact strongly. It's just weak interaction escapes from your collider. And then what you would actually be looking for, as I mentioned, is some missing energy. So far, this is kind of quite difficult to do compared to the other ways to search for dark matter. And so far, these detectors, in the collider searches, we haven't found the dark matter particle yet. But if we find dark matter with one of the other methods, this is really the way to get information about the particle nature of it and try to understand, basically get more information about interactions of dark matter. So finally, one of the interesting ways, the third way to search for dark matter is trying to directly detect it. So what do we mean by this? So we have these detectors which are operating underground. And then what we search for is the interaction of a dark matter particle coming into the detector with a nucleus in your detector or standard model particle. And then again, the dark matter particle would just scatter away, go out of the detector. But when it hits this standard model particle or interacts with it, it's going to actually cause some recoil in this. And this can be measured as a tiny recoil energy in the standard model particle in the detector. So usually we have like a nucleus, some sort of element in your detector, and then you have a nucleus where the dark matter interacts with, and the nucleus would basically recoil, and then you have some energy from there that you can measure. And so the idea is that you have basically billions of dark matter particles that can be passing through the Earth every second, but they don't interact very often. And in your detector, you, as I mentioned, you have a dark matter particle coming in, interacting with your target nucleus, and the nucleus would recoil. And what you measure is this really tiny recoil energy that you have due to the interaction of dark matter. And so these are really rare event searches. So you expect much less than 1 event in your detector per kilogram of detector material per year. So you have to have like ton scale detectors and run them for many years to have basically some events. And we have actually a lot of experiments, I'll talk about that, which are running around the globe currently. But you also have a lot of backgrounds. So you have to really go underground. And these backgrounds come from cosmic rays and also environmental radioactivity. So you really need to go in some mine or under some mountain and set your detector there. And you have to go several thousand meters below the Earth's surface to actually shield from all these backgrounds that exist. So these are actually a list of all the direct detection experiments that have been running, and some of them are coming online very soon. And so there is really a big effort and a really great endeavor for this. Here in Canada, we have all these experiments in SNOWLAB. So SNOWLAB is actually Canada's deepest underground lab at Sudbury, Ontario. And we have some new experiments coming online in SNOWLAB too. And at the University of Alberta in the Department of Physics, we have a number of professors who are involved with these experiments and working with them and trying to search for dark matter. So it's quite an exciting time with this as well. So dark matter hasn't been detected by these experiments yet, but if there is a positive signal in the future, what we can determine based on these experimental data we will have is the dark matter mass and also its interaction strength. So we can actually have a glimpse onto really what the nature of dark matter is. But still there are some ingredients that we have to know to be able to do these kind of studies. And the two important ingredients is actually we have to know how much dark matter there is around us and also how fast it is moving, because that enters in the calculations of the results of these experiments. So this is really like finding a needle in a haystack. So you have tiny interaction rates, you have large backgrounds, and we also have some uncertainties in the dark matter distribution around us. And it's just really been in the last maybe 5-10 years that we have focused a little bit more and tried to understand a little bit more the distribution of dark matter better than what we assumed before. And this is where also my research is focused on, trying to understand how much dark matter we have around us and how fast it is moving. So let's try to see what we know about this. So what is the dark matter distribution in the solar neighborhood? So these experiments basically are operating around underground the Earth. So we need to know how much dark matter we have around us. So we have actually a simple model. It's actually the simplest model for the dark matter distribution in our galaxy. Is just assuming that you have a sphere of dark matter particles. And in this sphere, you have the largest density of dark matter in the center of the galaxy. So this is just showing you the dark matter density. And here you have the distance. So the dark matter is largest here around the center. And then this density decreases as you go to the outskirts of the galaxy. Now in our solar neighborhood, the dark matter density is actually very low. So in particle physics units, which I don't expect you to understand, but just keep this number in mind, is 0.3 GeV per centimeter cube. So density is amount of mass per volume. And remember that the proton mass is 1 GeV. So this is less than a proton mass in every centimeter cube. This is still hard to understand, but if you consider a coffee mug, basically this is saying that you have around 1 dark matter particle per coffee mug. Okay, so the density is quite low. Consider all the protons you have or all the atoms you have in your coffee mug, which is huge, and you only have 1 dark matter particle there. And if you consider actually our own solar system, all the dark matter which is combined in the solar system is the mass of a modest asteroid. So, which is, you could see here the asteroid belt. So you have like 1 tiny asteroid, and that's all the dark matter combined. So we don't have that much dark matter actually in our solar neighborhood. And actually the way to measure that, there are 2 main methods to measure the amount of dark matter. One of them is using the velocity of nearby stars. So we can actually measure how the stars near the sun are moving and how fast they're moving. And that gives us a measure of how much matter we have around us. And if we know how much luminous matter we have, we can deduce how much dark matter we have. And another way is basically looking at basically trying to model the mass of the Milky Way, not only around us, but throughout the galaxy. So if you think about this as the plane, the disk of the galaxy, you consider basically the dark matter not only in one circle around us, but at different radii, and based on the rotational velocity data or rotation curve data that we have, we can try to get a global estimate for the amount of dark matter. And these measurements actually also have a very long history. They go back to the early 1900s, and this is a Dutch astronomer, Kapteyn, which he used in around early 1900s, used the measurements of this vertical velocity of the stars near the sun to calculate this local dark matter density, and he got this number. So this is actually the old measurements that we have, but the recent measurements with all the new astronomical data that we have is not too far off from this number. It has a range based on all the uncertainties we have between 0.2 to 0.8, but this number falls within this range. So we know rather well how the density of dark matter around us, up to some uncertainties. So the other thing that enters in the calculations to understand, again, the nature of dark matter and the particle physics is the dark matter velocities around the sun. So we can't really directly measure this. We can't use observations directly for this because we don't see dark matter, but we can use cosmological simulations to try to find what the dark matter velocity distribution is. So this is an example of one of the simulations. So this is showing you the gas. The different colors are different temperatures in a really large region here. And then if you zoom into some region and zoom in more, you actually see a galaxy which looks rather like our own Milky Way. And this is again like an image of one of these simulated Milky Way-like galaxies. We have an edge-on and face-on image coming from simulations. This is a newer simulations where you have a bunch of galaxies. Some of them look like the Milky Way. And this is also just showing you what the luminous matter in a simulated galaxy looks like. One of these simulated galaxies, if you can see it in three-dimensionally and how it looks. So we have these simulated galaxies. We can basically go to the position of the sun in these galaxies and then extract the dark matter velocities around the position of the sun and see what it looks like. And what we find is that there is a distribution of velocities. So this is just the number of particles that have a particular velocity. So if you have hundreds of particles, for example, let's say you have 70 of them having this speed, and then you have still some particles, but much lower number, which have smaller velocities. Some have much larger velocities. But most of the particles actually are moving with a speed of 220 kilometers per second with respect to the center of the galaxy. So this is just basically similar to the speed of the sun with respect to the center of the galaxy. So it is not surprising that dark matter particles are moving around that same speed, but they have this range of speeds. Most of them are moving around this speed. They're moving in different directions though. So you have actually all sorts of directions here for the dark matter particles. Now, this is not, so basically if this was the full story, you could basically take that and you could take the amount of dark matter we talked about, the numbers for the density, and then do a calculation for what, if one of these experiments actually measures some event or a signal which can be due to dark matter, you can figure out the nature of the dark matter particle, the mass of it, its interaction strength, and so on. This is not completely the full story because we actually have now a very precise map of the Milky Way. So this is the maps which is produced by a European space satellite called the Gaia satellite. And Gaia actually measured the velocities and positions of more than 1 billion stars in our galaxy. So we have a lot of information for the luminous matter. And here you see the Large Magellanic Cloud in this map. This is the most massive satellite galaxy of the Milky Way. So it is a smaller galaxy, so called a dwarf galaxy or satellite galaxy, and it is going around the center of the Milky Way. It is in its first passage around the galaxy, so it is coming in with large speeds. And basically, simulations again have shown that LMC can introduce a lot of perturbation to both the dark matter and to the stars in our galaxy. So just the movement and the passage of the LMC going here from the left to the right introduces all these perturbations and overdensities here and underdensities, because it gravitationally just perturbs the material which when it passes through them. Why is this important for dark matter? Well, LMC changes the dark matter halo as well. And then if you go back to simulate the effect of the LMC around our galaxy, you see that the picture I showed you before for the speed distribution, that it peaks around 220. This is not complete yet, because you have also particles which belong to the LMC, dark matter particles, which end up in our solar neighborhood, and they have higher speeds, much higher speeds. And this completely changes the prospects of these direct detection experiments or the searches for dark matter, because it can significantly actually affect these predicted signal in dark matter searches and experiments. And so there's still a lot of new things we are learning also from astrophysics regarding this, and trying to piece together what really dark matter is doing and what are the effects on the dark matter distribution close to us. So this is really recent research, by the way. So I just want to make an analogy of what we are doing as researchers to what maybe previous explorers were trying to do when they were trying to make a map of the world. So this is a map from 1570. And so you see that these maps improved over time, and all these explorers were trying to basically piece together different parts of this map as they discovered new territories. And this is similar to what we're doing. We're trying to map the dark matter distribution piece by piece. And when we get new data from observations, from simulations, and all of this help us to understand a small piece of this map, and then use this map to identify the nature of the dark matter particle, if hopefully we have some detection also in the future from all this great experimental effort which is going on. So just to summarize, so the evidence of dark matter comes really from a variety of different observations, but we still don't know what the nature of dark matter is. We know that it exists because of all this evidence. And we know that structures wouldn't form if dark matter was not there. So we believe that it should be there, but we still have not detected it. There is really a worldwide theoretical and experimental effort which is underway, try to unravel the nature of dark matter. Again, in Canada, we have large groups, important results coming up, and people working on this. And really, I think the next generation of the experiments, also the upcoming observations, and also future cosmological simulations can really help us unravel the dark matter mystery. So just stay tuned for that, and let's hope we'll have a discovery soon. Thank you.
Okay, so thank you so much. Do we have questions? And just raise your hand and I'll bring the microphone over.
I've seen and heard different opinions about whether there's dark matter in stars. So if there isn't, I'm just curious how there could not be. And if there is, does it affect the fusion reactions in the star?
So depends on what you assume for the interaction of dark matter with ordinary matter and with itself as well. But dark matter can accumulate in the center of the stars as it can be captured by the stars and accumulate in the center of the stars, but the amount is quite low. So it's not going to be huge, as you saw so it's not going to affect anything with respect to the fusions of normal stars. Now, if you consider neutron stars, which Sharon is working on, then it can be a different story. And then if you consider some, self-interactions for the dark matter particle, again, it depends on the model you assume theoretically for dark matter, and it can affect things as well. But if, for example, you have some neutron stars close to the center of the galaxy where the density of dark matter is quite high, then it can, have some important effect. Again, in our solar system, the density of dark matter in general is quite low, so we don't expect it to significantly affect, for example, our sun.
Are there any questions from Zoom? I see some comments, but I'm not sure how we would take the questions. In the meantime, raise your hand if you have a question you'd like to add. I'll bring that over. Oh, okay. Okay, Orla.
I have a question if
I'm just
can hear.
curious about the underground detection. Sounds very similar to neutrino detection. So how do you distinguish between neutrino interactions and dark matter particles?
That's a really good question. So neutrinos actually behave the same way. And so they are a background for these experiments. And they're basically an irreducible background. It's very difficult to surpass them, but they are below the interaction probabilities that we are currently searching. So the experiments haven't yet reached those interaction probabilities when they constrain the cross sections, in more specific words, the cross section of interaction of dark matter with ordinary matter. They haven't reached that neutrino background yet, but they will ultimately reach it, and it is a background for dark matter. There are ways to get beyond that background by, for example, neutrinos, if they're coming from the sun, then they have a specific direction. And if the experiment, our dark matter experiment, has directional sensitivity, so it can see where dark matter is coming from, it would be a different direction than neutrinos. So you can say the difference. We're not there yet, though. So this is future experiments.
So it looked like there was a question on Zoom. And I was wondering, Frank, could you, okay, great. I can't totally read it here.
Are you seeing my
Oh,
screen yet?
here we are.
Okay.
Can you read that yourself, or should I read it out loud?
Yes, so if dark matter is affected by gravity, why does it form spherical halos around spiral galaxies like ours? Why would it not also collapse into a large disk with spiral structure? That's a great question. So the difference between the dark matter and the ordinary matter is that ordinary matter also interacts with electromagnetism. So it can actually emit photons, and it cools, and then it basically falls to the disk and forms this disk-like spiral structures, whereas dark matter does not interact other than gravity. So it can have weak interactions, but in general, that's quite weak. It doesn't electromagnetically interact. So the only thing that can gravitationally form is these spherical structures instead of forming basically a disk that you would expect it to form if it could lose energy by emitting photons and forming these disks. So I can have a look. I think there are a bunch of questions, but I'll see if there are.
Hi, I really enjoyed your talk, but you talk faster than I can absorb, unfortunately. You say that interaction, when we look out into space, we know that dark matter has a dramatic effect on the universe and all the movement and so forth. And yet when it comes to detecting them, you say the interactions are very rare. That totally baffles me. Why?
There are two different interactions. So everything I talked about the evidence for dark matter was due to its gravitational interaction. That's at large scales, right? So gravity works, you see the effect of gravity at large scales. It's quite weak in small scales. So that's why, like this chair and I standing here, we don't gravitationally attract because it's basically small scales and the masses involved, right? But if you go to large masses like the Earth and the Sun and everything in the universe, then gravitationally, that's all the evidence we have for dark matter and all these structures form. Now, in the lab, it's the effect because we are working with these tiny particles that are interacting with some very tiny nucleus, which is made of some protons and neutrons. So these are all elementary particles, right? That we are considering the interaction. We're not considering gravitational interaction there, but we're considering this weak interaction, which is a different type of interaction. It has a very small range, and these interactions are quite weak. And so you basically you have it's very rare to have these interactions happening you have to have really large masses of your detector and let it run for multiple years to basically see one of these effects. So it's two different types of interactions. I didn't go into all of that in detail, but so far we don't have evidence for the weak interactions, just it's a hypothesis that we have for dark matter if it's made of these weakly interacting massive particles, but we know that it should interact gravitationally, and that's why all those structures are formed.
I see one question from Bruce says, you said dark matter in a galaxy can move in any direction. Is it random, or is there a preferred direction, like towards the galactic center?
No, there's no preferred direction. So they're all moving in different random directions. And you saw some of the simulations that I was showing you. If you consider those as dark matter particles, they were kind of moving around basically.
I have a dumb question. Newtonian dynamics is something we well understood and calculated. If there's dark matter in the presence of our solar system, wouldn't there not be some third order effect or something that we would see in the motion of the bodies in our solar system that would be affected by it?
That's precisely what it does. So that is the rotation curves that I showed you. So basically, due to the dark matter that's present in the galaxy itself, due to the dark matter, and not the solar system is actually also as well, it is causing the speeds of the stars and the gas in the galaxy to be larger than what you would expect if there was no dark matter. So there was actually a compilation of all the measurements of these rotational velocities of gas and stars in our own galaxy done very recently, like a few years ago, where it put everything together and you could basically see how much dark matter you have at the position of the sun. And this is what I talked about, is also based on all the evidence that we have. So it does affect the speeds of everything close to, from the center of the galaxy to outskirts of galaxies.
What I was saying though is, can we see an effect on the motion in our solar?
Oh, the planets. So the effect would be quite small on the planets. So you, because we don't have, so the density is quite low. So it wouldn't drastically like change the planet's motion basically, but you could see it from again the observation we have of the motion of stars and the gas particles and other things. Yeah. Arnold has
my question is like, has there been I may have missed it, but is there a model that you have or that the studies have in terms of what kind of interaction you can detect using that direct method? Would you be using, like the Sudbury Neutrino Project looks for photons or whatever when neutrinos interact with with the atoms? What kind of a model do you have for?
Yeah, so
dark
for
matter?
example, the main model is this WIMPs or weakly interacting massive particles, which you assume dark matter, in addition to gravitational interaction, has weak interactions. So it interacts via the weak force or around the same scale as the weak force. And that is one of the well-studied models that we have. Yeah.
Are there, oh, one more question here. Oh, oh. Sure. Yeah, you're special.
Quick question. Is there been any relationship determined between dark matter and dark energy?
Not that I know of, because they are quite different. So dark energy, again, is a form of energy that we don't know really. We know less than even dark matter about, that it's responsible for the acceleration or accelerated expansion of the universe. Yeah, not that I am aware of that you could directly relate the two, because this is the missing mass or invisible mass that we have in the universe. That is a form of energy. So yeah, maybe we would have something in the future. I'm not sure.
I think we have one last question.
Yeah.
Yeah, thanks for the excellent talk. You mentioned that dark matter can undergo weak interactions. Does that mean that if there are atoms of dark matter that they could undergo radioactive decay mediated by W and Z bosons, and then would they emit photons, and would those photons be also dark?
That's an excellent question, and getting into the realm of the theory. Actually, yeah, you can have, there are theories where dark matter, you have similar to the standard model of particle physics for ordinary matter, you have also dark matter. Dark matter is composite, and you have dark photons, exactly as you mentioned. You have, you know, the mediators between the dark matter particles can be similar to the W and Z bosons, but the dark W and Z bosons, so all of that. So, and you can search also for these dark matter particles as well. So with colliders, I mean, if in one of the direct detection experiments we do discover something, then we have to go to colliders to really get information about what the particle physics nature of dark matter is. But yeah, that's an excellent question.
Thank you.
Okay, very interesting stuff. And go figure, the lab from Canada is called Snow Lab. Okay, just before we go for break, oh, I saw my agenda up there. Frank, can you click on just above that, the astronomical trivia link? So just before break, we'll do a little trivia. Can we see that? Anybody see that? Ah, there it is. So just before the break, today's astronomical trivia is, which constellation contains the most Messier objects? So that's something for you to gnaw on during the break. We have about, it's about 8:30. So how about we'll reconvene in about 10 minutes at 8:45. Okay, all right.
Okay. All right, well,
Okay, sorry for the little delay there, just getting things going. So again, a few months ago, Orla has offered to do a little musical interlude for us, and it's proven very popular. And so he's here for another one.
thank you very much. So just to introduce the presentation a little bit, since I picked up the guitar in high school, I've composed several songs just as a hobby. Mostly I sing and play in private. It's more relaxing. I don't have to worry about the audience. I get kind of stage fright when I try to do it in public, so that's not so. Anyways, about 20 of my compositions have some astronomy content. And since, and these star tunes I have been presenting to this audience since I think November of 2021 via Zoom. And tonight is my 13th presentation. I'm not a professional performer, so don't expect perfection. But when I retired in 2020, I decided I was going to also learn how to play the keyboard and instead of the guitar. So with this presentation, this is my first attempt at putting my guitar aside and using my electric keyboard in my basement, where I used a piano and accordion, flute, and some rhythm drums to put one of my songs to music and re-record it. I have to thank Sherilyn Jarek for providing me with some excellent piano lessons. I don't know if she's here tonight, but she's an excellent teacher, and I just wish that the presentation would do her teachings justice. But anyways, without further ado, here's the song. I think. Hit the space bar.
Nuclear war, runaway climate change, a global pandemic, an asteroid impact. Today, we face all manners of threats to our continued existence. However, Earth's ultimate destiny is to be baked, blasted, and eventually disintegrated by our evolving sun. Our sun enabled life on Earth to evolve and flourish, only to be eventually obliterated when the sun advances through its red giant phase. If we want to survive the sun's death, we will have to eventually abandon our childhood home. And go where? Perhaps to Jupiter's moon Europa with its abundant liquid water ocean. Or perhaps we can become interstellar travelers. Should we somehow survive the sun's demise, then general relativity and astronomical observations suggest that time and space, and perhaps humanity, will continue forever. But this song is not about the end of time. It is a song about the sun, or finding love, while we still have time. Your flames are burning true. They warm my heart and soul. You are my fire until the end of time. Until the end of time. But in the dark of night, all that is left of you are just the sparks from your fire. the night for you. It is my passion, because my love is true, It is my destiny, I'll never tire until the end of time, But in the dark of night, all that is left of you are just the sparks from your fire. When you rise for me, I am waiting, because your warmth is free. Within your solar winds, I will be sailing until the end of time.
Right to the rescue. Thank you, sir. Okay, thank you, Orla, for that. So our next presenter is Mark Zalchik with Book of the Month.
Yeah, I've got proof that Jay likes to share, because Jay and Daisy have just donated a book to the library, Planetary Astronomy. Thank you very much. And it'll be available to members to rent at the end of the meeting, as well as the Book of the Month. Do I have an image of it, or actually I got it right here. I could just show it. So the library is just located off the main entrance to the Star Theater. It's open before and after each of the meetings. As far as this month's Book of the Month, in a handful of localized areas around the Earth, strange glassy rocks have been found. These tektites often take on exotic shapes like buttons, teardrops, and dumbbells. Some emit a magical ring when struck gently. Early man used them as talismans. Tektites were first described in written records by the Chinese in the 10th century AD, where they came to be known as the Legong Mo, or ink sticks of the thunder god, or Legong Shi, the stool of the thunder god. I'm thinking stool, they're referring to furniture, or maybe not. Not sure if they're referring to furniture or whatever, but I plugged these same terms into the translator and got respectively race cemetery, and it doesn't matter. So the translations was lost somewhere. So March's Book of the Month is the tektites in the geological record, showers of glass from the sky. The book is donated by Murray Paulson, and it delves into the nature of these fascinating objects and how they are the result of large impact events in the distant past. So the book will be available right after the meeting as well. And also what we'll do tonight is at the cookie table, I'll have the book available for people to browse. And Murray and I have actually brought some samples of tektites that you could have a look at as well. So that'll be just at the table here right after the meeting. And otherwise, feel free to go into the library and look through the books. And if you're interested in one, just bring it back up and I'll just write your name down on the card. All right. Thank you very much.
Thanks, Mark. And thanks, Murray. Right. Okay. Next on the agenda is Abdur and our Astro Imaging Corner number 126. Do I hand over, stop the share, Frank, or?
Thanks, Jay. So I'll see if I can share my screen and just let me know if it shows up. Okay, can anyone confirm if they can see that?
Yep.
Perfect. Thank you, Murray. Okay. So there we go. So I think this might actually be Astro Imaging Corner number 127. I'll have to double check that later. So for anyone joining us for the first time, Astro Imaging Corner is the part of the regular meeting where I share all the images that have been sent in by members. So thank you to everyone who sent it in or who sent in some images. And if you didn't get a reply from me to your email, just know that I did get your images and I did get to see them. I just haven't gotten back to replying to all the emails yet. And for anyone who might want to send in images, you can go to the RASC Edmonton website, and at the bottom left, there is the Astro Imaging Corner link. So you can click on that and then attach your images there, and they will show up in my inbox. So the first image today is from Tom Owen, and this is the Rosette Nebula, also known as NGC 2244. And this is in the constellation of Monoceros, the unicorn. And this was imaged between February 17 and 19 using a TS Optics 90mm triplet refractor at prime focus and Tom's QSI 683 CCD camera. And this was a total of 7 hours of exposures in hydrogen alpha, oxygen, and S2 using 6-minute sub-exposures. And this was stacked using APP and processed using STAR tools. And Tom said he's been very impressed by the little TS Optics 90mm triplet. And the next image, also from Tom, is Thor's Helmet. This is an emission nebula in Canis Major. And this image was taken on February 7th through the same TS Optics 90mm triplet telescope. And this is a total of about 3 hours of exposures using the same filters and the QSI 683. And this was again stacked in APP and processed using STAR tools. So very nice shot there, Tom. And up next is one of my favorite objects in the sky. This is Messier 46, also from Tom. This is an open cluster in the constellation of Puppis. It's quite low from the sky here, kind of near Canis Major, near Sirius, but very low in our skies. And this is a rich field region and sports a little planetary nebula within that open cluster that you can see just above the center. And apparently it's not part of the cluster, but it's nearer to us and thus superimposed on the image of the cluster, according to Tom. But that's still very cool. And this image was taken February 15 and is the result of 12 1-minute subs in LRGB for a total exposure of 48 minutes using the same 90mm triplet refractor and a Takahashi 1.6 focal extender. And again, processing and stacking was done in the same tools as the other pictures. So again, beautiful star colors and very, very nice capture, Tom. Up next, we have an image from Stephen Portillo. I believe this might be Stephen's first image. And this is of Venus-Jupiter. This is of the Venus-Jupiter conjunction on the evening of March 2nd, taken with a Nikon J1. And actually, yeah, Mars, Venus, and Jupiter should be visible in this image. So a nice shot, and thanks for sending it in. And we're hoping to see a lot more images from you in the future as well. Up next, we have an image from Jonathan Porter, and I believe this might also be the first image I've received from John, so great job on this image. Jonathan is an RASC member and became interested in visual astronomy in 2020 and started getting into deep sky astrophotography last year. And he said that this image was what really got him hooked on astrophotography, and it was taken on January 24, 2023 from his backyard in Edmonton. And the equipment used was a full-frame Canon EOS R camera with a CLS filter and the Teleview 85mm refractor. And it was for capturing Celestron CPWI, PHD2, APT, Deep Sky Stacker, and Photoshop were used for this image. And this is a total of about 90 minutes of exposures, and individual subs were 60 seconds each. So great job there. And again, hoping to see a lot more images from you in the future as well. Up next, we have an image from Hans. This is the Rosette Nebula in narrowband, and this was taken with a one-shot color camera from Sherwood Park in Bortle 7 skies. And Hans used the Optolong L Extreme filter, which provide the hydrogen alpha and the oxygen, and a Baudelaire 7 nanometer narrowband filter for the sulfur. And the telescope was the ASCAR FRA 300, and the camera was the ASI 2600 MC Pro. And Hans acquired several 5-minute subs for a total of 120 minutes with the L Extreme and 90 minutes with the sulfur filter. And this was processed in Serial in GIMP and Topaz AI. And again, the stars were added from an earlier broadband acquisition that Hans had taken after first removing the stars in the narrowband stack using StarNet++. Again, beautiful shot there, very nice wide field view of this region. Up next, we have an image from Josephine. This is the Bubble Nebula region. And this is a total of 55 lights at 90 seconds each with Josephine's Nikon D50-300 camera, and the scope was the White Cat 51. That's a 250 millimeter focal length refractor, and Josephine was using the Star Adventurer mount, and this was stacked in DSS. And this is the first try for Josephine with Serial for editing, and then GIMP afterwards. And this was taken January 31st in Mondare. So beautiful shot there, very, very nice. Up next, we have another shot of the Rosette Nebula from Brian Martin. And Brian said that sometimes astro images make him see red, literally. It's easy in post-processing to overdo the red emissions from the hydrogen alpha nebulae. And of course, we are all guilty of that sometimes. And Brian says that while you get a dramatic picture of the faint nebulosity, it's not an accurate portrayal of the color balance present in the scene. And this almost always destroys or distorts the colors in the stars in the image. So one of the most significant recent additions to PixInsight is the very powerful SPCC tool. That's the spectrophotometric color calibration tool. And yeah, I always use that for color calibration as well. It's a very good tool for anyone who uses PixInsight. And this is a total of 6.7 hours of data on the Rosette Nebula through LRGB and hydrogen alpha filters. And this image was taken with the ASI 1600 and a StellarView SV102R telescope on a Paramount MX mount. And now the beautiful tones of the many different spectral type stars show up, notably the concentration of late O stars in the central cluster, which is NGC 2244, as well as the number of lovely amber or late red K and early M giants in this field. So again, yeah, very, very nice colors and beautiful shot there. And Brian is also the professor emeritus for physics and astronomy at the King's University in Edmonton. So it's always nice to have some actual professionals as well among us amateurs. Up next is another shot from Brian. This is the Milky Way from Turret Arch in Arches, Utah. And this was taken with a Canon 6D and a Samyang 35mm 1.4 lens. And the stars in this image are a sum of 4 2-minute tracked exposures at ISO 800. And the foreground is a 1-minute shot at ISO 3200. So beautiful shot and very nice composition. Up next, another shot from Brian, and this is the Milky Way from Monument Valley, Arizona. And that's the Three Sisters on the right. And this is from a September road trip through Utah and Arizona. And this was again taken with the same Canon 6D and the Samyang 35mm lens. And this is a total of 6 exposures of 2 minutes each. Up next, we have one of my solar images that I'd taken the data a while ago. I just never got around to processing it. But then I saw the email on the Astro list asking for some images. So I quickly ran it through AS3 and Registax. And this is the sun in hydrogen alpha taken with the Coronado PST 40 millimeter solar scope and the QHY 462 camera. And you can see quite a bit of action going on there as we're getting close to solar maximum. So I'm looking forward to the next couple of years. And the last image of the night is one of mine as well. This is the Horsehead Nebula. And while I was troubleshooting my main astro camera, I was testing out the Fuji XS10 mirrorless camera on my telescope for some testing. So this is a total of about 1 hour of 60-second exposures. And it turned out pretty good, although you can see some of those weird spikes on the stars, and those are caused by the power cable that I was using to power the Fuji mirrorless camera that night, because in the cold, the battery would have lasted maybe 20 minutes without any external power. And this was entirely processed in PixInsight. Yeah, this is just a one-shot color unmodified camera. So that's it for tonight. So a huge thank you to everyone who sent in some images, and I hope to see more next time. Okay, have a good night.
Okay, thank you, Abdur. Again, the skill level coming out of this center is absolutely amazing. Okay. Yeah, again, some amazing pictures coming out of this center, and keep them coming. So it's really quite the treat to see what our local talent can do. Okay, just into the home stretch now. So on the trivia side, we'll do our answers there. So again, I wasn't sure if everyone could actually, that was not the trivia. Just to be clear. Okay, so can everybody see that? It looks much better on the computer. So which constellation contains the most Messier objects? Do we have anybody want to shout out what they think it is? Sagittarius.
Virgo.
So we'll just jump here. So that's right. So Sagittarius is correct. Moniker for Sagittarius is also known as the Archer. What's the best known asterism in Sagittarius? The teapot. That is correct. And how many Messier objects in Sagittarius? No. 15 Messier objects in Sagittarius. And who can list them in chronological order of discovery? Just kidding. Whoa, geez. I was kidding about that part. But what I did want to point out was the one of the objects, Messier 54, is an actual extragalactic globular cluster. So I didn't even know that myself. So pretty low though in the sky from our latitude. So generally, if you want to catch the bottom objects like 54, 55, I think, and 70, you usually have to head south for that. Okay, so a few upcoming events and announcements. Frank had one.
Just a really quick announcement. If anybody's interested in helping us out at the observatory, we're looking for some new volunteers to help us operate the RASC observatory. We would like to open up on other nights. Right now, we're doing Friday and Saturday nights. We're going to start opening up on Sunday nights because Chris Marivold and a few others are able to open up on Sunday nights. But if anyone's available to do Saturday afternoons or Sunday afternoons, want to learn more about using the solar telescope at the observatory or try some of the new fancy camera gear we have out there, just contact our person here at the Science Center who looks after our volunteer recruitment. Her name is Brittany, and she can get you started, and we'll get you out there helping us out at the observatory. So if you do have an interest, wanting to learn more, you don't have to know everything already. We take anybody that just wants to learn more about using telescopes and observing. So I'll leave it there. If you have any questions, just come talk to me after the meeting.
Okay, thanks, Frank. So some upcoming events. So March 15th is our Astro Imaging Astro Cafe. And I just want to give a shout out there to Richard Covey, who has taken on the Astro Imaging Cafe, I guess, coordinator. And I just, so a shout out to Richard there that, you know, he's trying different and innovative ways to help advance members' skills in astro imaging. And I think he's come up with a really good idea for this March 15th event where he has provided some raw data and asked the local astro imagers to process that data and then present your results at the March 15th Astro Cafe. So all range of skill is welcome to participate in that. And again, it's a great way to advance your own skills. So if that's an interest of you for you, then please attend. And any other feedback that you may have for Richard. So again, he's really looking to help the center and advance folks' skill in that regard. So by all means, let Richard know. April 5th, we have the famous, legendary What's Up Over Edmonton by our own Jeff Robertson. And again, I don't mean that in any bad sense, because it is actually a very interesting, informative, and Jeff always makes it entertaining hour. So if you have an hour, you have to attend What's Up Over Edmonton. John Stolt and I believe Berta will also be hosting the Observers Group on April 12th. And sorry? Oh, and thanks, Sharon. I'm gonna go through the last piece of it, but in April 29th is International Astronomy Day. And if folks read in the Stardust that was put out yesterday, Council has discussed, and we would like to do an event for International Astronomy Day. It's just been way too long since everyone at the center has gotten together collectively under the sky. And so we're looking to do that out on Coronation Field here out by the observatory. So everyone is welcome, and we will be inviting, of course, the public out as well. And we will do a telescope clinic and quite possibly do some food trucks or something like that as well. So we'll make it a daytime and evening event for sure. So put that in your calendars. I hope to see everybody there. And finally, as Sharon mentioned, our next meeting, monthly meeting, is on April 17th. Okay, so that's it. Appreciate everybody coming tonight and everybody that contributed. It was a really good meeting. And so it is 9:25, and I call the meeting adjourned. Have a good night, everybody.